Welcome, ladies and gentlemen, to this video. So today I wanted to make just a review about all the different projects that I've been working on lately. I've made some beautiful progress in many different directions, and so I just want to keep a vlog about the different projects that I'm engaging with. Now, I do want to say before I start that I have paused my music endeavors, and they will likely be paused for a duration of about 6 months or so, where I'm going to do it more in a playful or hobbyist fashion instead of a direct programmatic recording system. Um, there's a few different reasons for that, but let's not go into this for now. I just want to focus on this engineering and sketching CAD software. So I've been focusing on that since I did achieve the a level of recording that I wish to undertake. And so now I decided to shift my focus to be more specifically oriented towards the development of robotics. There's a few different mechanisms that I think I can greatly participate in the development of by adding a few different, perhaps unexpected ideas about different mechanisms inside of robots and their anatomy. So I do have a lot of different ideas I want to explore, so much so that it has taken the forefront in my time, meaning that it's the first thing I think about, and that's what I dedicate most of my present or current effort to. So in this intent, I wish to just go over a few different systems that I've been working on. Some of them are really beautiful. So let's dive into it. So it's going to be quite a long video, I'm going to tell you right now. I'm looking for maybe 15-20 minutes, if not more. So if I just go to the left side of my screen, this is the one that I have worked on today, this morning. So this is a biomimetic tension web system. Call it the wrist of Prometheus. This is a system that's built to utilize string in ways to reproduce the human body. It's going to be both a cross of high artistic consideration of human anatomy and functional robotic parts. Now, it does require quite a bit of work and definition to get all this done, but it's going to get done, and it's absolutely beautiful. So, but still at the beginning stages of the project, so this might take maybe 6 weeks to complete. But I'll see when I get there. So first, let's start off the last time I left off. So last time I left off, I was dealing with some advanced geometry. So I call that the tetrahexum or tetrahexium, which these are basic. These are kind of universal Lego blocks that enable me to create any kind of disposition of skewers and pins and connection point lines. So I can use a structure like this to, if I have a conjunction of multiple of these, I can create kind of a web, and it's kind of cool because it looks like a molecular web, and I can basically create any kind of distance I need between two axes. So if I want to test, say, the leverage of the hammer in multiple different positions when I create the piano mechanism for the vasculary systems, then I can use a piece like this to create a setup and have different systems to test. So I can test the counterweight, I can test leverage ratios, the position of the pivot, and all that stuff. So this is a piece. So I print like, I don't know, 30 or 40 of those, and then I can create whatever adjustment I need and then produce the right position for the axes that I need for whatever test that I want. So this is an interesting part here. Here, the second one is going to be the ball joint chain. So I wanted to see if it was possible to create the ball joint and the tolerances necessary to make it happen. So this is what I came up with. Hold on. Okay, so I've got this cavity here inside, and you can see it's kind of odd. It looks like a Star Wars. You know these Senates in the Star Wars? It looks a little bit like this from the inside. But anyways, so I tried to go with the tightest tolerances I could. I ended up figuring out that the tightest tolerances that I can print while still maintaining mechanical functions is about 0.2 millimeters. But that is also very at risk of having printing failure issues. So if I make a print and there's like a gap, or there's a layer that doesn't stick, or there's an issue in the layering, maybe like there's like 5, 10, or 20 different layers that will have some kind of a delay or phasing. And if that happens and the tolerances are too tight, then the print doesn't maintain the mechanical properties. So in my practice, I find that if you leave a gap of zero point 0.5 millimeters for any part, regardless, the print is going to function mechanically with that kind of tolerance. But I needed to do a test like this to figure this out. Now I wanted to try this out and see if I could create kind of a omnidirectional joint, so I created this. That was an interesting test, but there is not that much to it. So then, yeah, for the vasculary system, that's one of those that I made a lot of different progress in. So I'm going to go over that in a different video. So I want to put that aside because it's substantial in and of itself. I don't want to go through that right now. So this is an interesting one here, and the wave disk is also a very interesting one. Put that one aside for the minute, but so this one here is a system that's based on the golden ratio. This one, you can see there's a bunch of different holes, and it's made to allow me to test the different weight or positions of pulleys, so I can tie pulleys to these holes and then put them in a system on a common axis and witness their effect with gravity or position in space. It's a kind of versatile thing, but I didn't do too much experience with this right now. Eventually I'm going to imply this in the piano mechanism, so to create different kick responses by varying the position of this in space, but that's still under development. So let's put that aside for now. Let's go into wave disk. So the wave disk, I think, is a very interesting piece. Now, it doesn't seem like much, you know, you look at that and it doesn't strike as a very useful piece of plastic, but there's something very interesting about all this. Now you can see that there's a bunch of joints over here. The idea behind this one is to translate the movement of a snake in a circular system, meaning that if I spin this around, I want to achieve the same movement as a snake. And so my vision for that was I was imagining a robot, say in a Star Wars or sci-fi character, that would, well, yeah, you can see all the different parts I've got on my background here. So I wanted to create a piece that would enable a robot to traverse space while waving the disc or spinning the disc to mimic the movement of a snake, and it would create this very elusive, also organic type of movement that would be quite different from a standard wheel or from an average movement mechanism. I thought it would speak to a very refined and elegant way to move a robot through space. So I tried this. Now this is still just a test. I know it's possible to make this happen if there's multiple waves. So if I have like a disk with maybe 8 or 9 waves, I have to warp the structure a little bit, and then I can achieve a steady movement from the spin. I wanted to start this project off with a simple form so that this way I could explore with how to tilt the wheel as it spins in order to create different traction patterns on the ground. Now that would imply to have different friction ratios on different parts of the discs, so to obtain that. So as the disc would spin rather slowly, it would tilt from side to side, so to get on those high friction patches and move forward. Now there's a lot of development that needs to be done there, so that's still a very nascent idea, but it's a pretty good one, I thought. So that's one of the things. Going up next. So this one is at the base of many different developments. So this one here is in conjunction with the printable bearing. Now the printable bearing is a very important one. So I wanted to find a way to create prints that would be, or bearings that could be easily 3D printable, so that I can reduce the assembly time or the size requirement to imply bearings. So it can get really tricky with bearings because there's all sorts of sizes and details that are implied in bearings. There's different types, there's angles, there's one with cones, rollers, balls. It's very complicated. So I thought if I can get a way to create a very small form of a bearing then I could create 3D printable parts that have mechanical systems embedded in them simply by using accurate geometry. So the first, it took quite a few of those to function. So this V6 you can see here, I don't have the first few ones because it was an iterative process. So I would make one, delete it, or it did the parts and go back and forth like that. So I managed to create this one here, which was printable, although they're very tight tolerances. You could print this one, and it had also a casing. Hold on, where's the casing? Yeah, so that's the casing. Okay, so yeah, so that looks like a very standard bearings. You've got the rollers inside of it. You've got the casing that makes sure that the bearings can't escape. And so as you print it, then you have these rollers that are embedded in the part that you can't remove. So I tried this part, and it took a few prints before I managed to make it work. And this one was functional, so I was able to use it as a bearing. However, when I look at the size of it, it's a little bit large. So you can see 15 millimeter. Bearing outer shell size, so it's pretty big. Now I tried to imply this in this Alvin Stewart platform. Now this is just a basic sketch for the mechanical properties. Um, so I just wanted to see what it would look like basically before I would go into a more elegant style. And you can see here that the bearings are put in the joints so that it can move already simply by printing it. Now I've tried those prints, but as I was about to print something like this, I thought I could really enhance the printable bearing. So I went back to it and made printable bearing 2, which was the next generation of those. And this one I think is exquisite in many respects when I consider the fact that it has an extremely simple geometry. And it's a principle that you can scale down to an absurdly small number and still maintain its relevant properties. And so what are those? So if I go in here and look at the bodies, I'm going to take out the inner side. So this is the outer shell of the bearing. Now you can see this fluted inner cavity. This fluting inner cavity here enables me to have a low surface of contact, so a line that goes across the circle will contact the inner inner tube, and that will cause. So maybe I'll go into a wireframe mode so you can see it better. Okay, so this, just keep the sketches out. Okay, so you can see here now the insides. So the outer shell bearing, this is the outer shell of the bearing, has this fluting effect, and it reduces the friction with the inner part, and there is a clearance here that is about 0.5 millimeters, and so you can print this maintaining it upwards like this, and you can print it, and as after it's printed you can spin it, and it runs really effectively. It's quite surprising to witness how freely it spins. So now the outer perimeter of the whole device here has a radius of or a diameter of 8 millimeter, which is a lot smaller, and also implies a central axis of 3.5, which connects with all of the tetrahexene parts that I was talking to you earlier. So I can pass a skewer through that and connect it to other parts. So it can go even smaller than that using simply this geometry, but this is the smallest one that I find very practical. Now, how do I use this, or what do I use it for? I'll show you this in a second. So I think that was a very important step forward in the development of robotic parts, because now I'm stepping into a realm that's more about mecha geometry, meaning mechanical geometry, which is very interesting. So let's put that aside for now. Now this Stewart platform, which was the first iteration, I managed to go to the second iteration, which is this one. It's very important to always start with some basic sketch or basic parameters in order to then refine it, because if I want to start with the aesthetic compound or properties, it really is difficult to figure out how to move forward. So the bodies. So, this is my Elvin Stewart platform. So the Stewart platform has three different arms, and if you manipulate the angle of each arm, you can basically produce an extremely predictable object. So this is often used in robotics for assembly line or robots that have to say take an object and move it from one place to another. It's going to use a system like this that has two joints connected to a triangular base, and also the those ones, the end clips, the end fingers, I should say, are also connected by a platform. And by manipulating the angles of the hinge, you can produce just about any position you want, which is extremely useful. So I wanted to make it, but with a higher aesthetic consideration. So this is what I made here. Now, I could have embedded a 3D printable bearing at the base, but it would not fit on my printing platform very accurately unless I would need to do some significant change. Well, I could, but I decided not to go through that. So I decided to keep the central part with a skewer connection here, but I did imply a printable bearing in the connection of the arms here. So you can see the fluted pattern that was derived from the printable bearing. So this one here, this part, so you can see here that there's this connection here is done through geometry, and it does create a stable axis. I'm missing something here. Maybe I just did it on one. Oh, right, I think I put the bearing right in there. Yeah, that's what I thought. Okay, so the bearing's actually present in there. So when I export it, it simply like integrates. So you can see the clearance here is 0.5 on each side, and there's the axle going through, and the geometry is nice and stable and effective. So the axle is right here. So that joint here is simply printable, so you can print it and it spins, which is kind of nice. And then you have this filigree pattern for the legs, which I thought was very interesting. I want to approach robots not with just the idea of making robots, but bringing robots to an extremely high level of refinement. And I'm going to reach that aesthetic property or quality later on when I go back to this one in the background you see there. But I have many different other projects to go through. Like I said, this is going to be a long video, so I'm expecting another 10 minutes at least. So after making this Stewart platform with the Elvin designs, the joints were functioning properly. However, there was an issue, and it was that there was not much control or suspension in the joints, meaning that the joints were so free that they would simply fall with gravity and not have any kind of inherent mechanical structure to them. And by this I mean that there was no restriction on the movement in any possible way. So if I'm trying to make a Stewart platform, there's an angle at which I don't want the fingers to extend. I don't want the fingers to overextend. So I need to try a bunch of different systems to embed in there, so to have a higher control on the degrees of freedom of that connection. So although the printable bearing was efficacious, there's a lot more that needs to be done. So I started to make a series of tests into different types of joinery that I could embed inside of those joints. And now the joinery that I wanted to work on, I call that tendon and bone joinery. The tendon and bone is simply based on the it's a biomimetic idea, and by that I mean it's mimicking tendons and bones in physical in your body, meaning that the connection, say, between the phalanges and your fingers would operate in similar terms. Now, I decided to make a series of 10 different experiments in order to test how I should go forward, because I had many ideas that I wanted to test. So I started here with this system. This one was not very good. This was quite of a failure, because I thought, okay, I'm going to need a way to tie the rope and then pass it through channels in order to stabilize the joints. This way I can add constraints to the joint by using the tension of the string as a tendon. Now, this is my first iteration, which was poorly made. The channels here are too tight. I thought it would be nice to have them tight so that it would restrict the string, but it made the assembly quite difficult and not useful. And then I thought I'm going to have cleats multi-directional cleats at the end, so to help, but it turned out that none of that was really useful. So instead, I tried the number 2, then number 3, number 4. Okay, so this one is based basically on the first one. I thought maybe I don't need to have as many cleats or parts. Maybe I can just create these loops where I can pass a string through and then have 2 of those side by side or mirrored, and then have the connection between the parts simply be dictated by the string. So I would roll the string around, tie it to the back, then pass it over the other loop, tie it, and that mechanical connection between the 2 extremities would be would make a joint or an axial connection, where the circular parts would kind of conflict with one another. So it's like hold on, I'm not gonna do that. Never mind. So it was basically 2 of those parts mirrored with string connections. Now that was a very useful joint. The properties of that joint, I think, are very useful in many respects. It mimics a bone, the knee structure and how the knee moves along its edge, but a little bit more freedom because it's like 270 degrees of freedom in that axis because it spins almost a full circle. So I thought that was a nice experiment, but although not very efficacious, this cleat system is not the best. It wouldn't function very well. So I made the next experiment. Now the next experiment, I wanted to try something else. I wanted to also do some linear work. So if I look at the phalange in my finger, I thought maybe I could create a phalange with some holes that if I pull a string through them, I can then create predictable movement, just like your tendon in your finger, where as you pull your tendon, the finger contracts. And now to do this, I need a series of channels that would direct the string to pull and fold the mechanism appropriately. And so I thought I'm going to start with a straight bone or member and then see how it goes. I tested this one, see with a few different angles how the pulls or pushes go and how it would function, so how to interlace the string so to create the predictable movement, but it wasn't really good, so I had to do another one. Now then I started to move into a different level of understanding of the same components. This one here, I decided to let go of many of the cleats. I decided to replace the cleats with a series of holes that are well situated, because the holes that are well situated would act as a cleat during assembly. So as I pass a string through those, it creates this mechanical connection where the parts are forced to interact. But then I can also use a separate row of circles and use that as the binding point. Now the way this is done is much more useful, so I can bind them, create knots, and then use CA glue to seal them, which is so much more useful. It speeds up assembly by about 5 times or so. Makes it much better. I also have these grooves here that really help to orient the string, and I also have this outer line here, which this one I had to edit later on. Not very useful to have this with the outer opening. It's better to have it closed like this because I can create knots. Here I can't really make knots. Although it seems useful from the top, meaning that it looks like a cleat shape, what happens is that when you start to move the thing around, tension has a lot of variation in the system, or the string has different loads, and sometimes it bends or slacks, and then it can pop out of the cleat-like ending, so that's not good. So then I thought I'm gonna try to go closer to a real knee joint. So this is the experiment I made. I thought I'm gonna go as small as possible, but still functional, and I'm gonna base it on the exact shape of a knee. So the knee has this type of connection where you have this large circular bone and this small circular bone with these grooves. So this is kind of a geometric interpretation of a knee in many respects, but it's really based on the knee. So I thought I'm going to create it as small as possible, and I was able to create it. I mean, this is quite small. Hold on. If if I consider the outermost points, that's 11 millimeters across, which is quite small. I could go a little bit smaller if I optimize a few parts, but it turns out that this one is really not the best because the channels are not made right. And although it does work as a joint, and I have to consider this intersecting shape at a later point, this I thought was not really the right way to go. I thought I could make it better than that. Now I put this one in tendon and bone, which is not really the right way to go. I wanted to see how I could operate different forces on a single axis. So I thought creating this experiment here would help inform me about how to deal with the force distribution in the circular pattern like this, or a radial pattern. So if I tie the rope in the inner circle and then tie it to the outer circle, then I can manipulate this and treat them as a mechanical axis. I put it in the tendon and bone because it's a little bit like a shoulder system, I'm thinking about the scapula type thing. And then if I use the bone and tendon, I can create predictable motion by pulling the string, which does fit in that type of joinery. But the thing is, this also has other applications that are outside of the tendon and bone. I'm looking to use this in the vascular piano system for some specific parts, but I'll go over that in a different video. That I thought was a very interesting one. I do recommend you try printing a part like this. It makes a big difference what you can do with half circles like that. These are two indented circles. I could make more, but 2 was enough. So then I moved on forward. I optimized the joint I spoke about earlier with that 5-threaded thing. No. So this looks familiar. It looks like the other one. You can see here that there's this fluted intersection, so to reduce the friction. And you can see the channels are much better defined. This is nice and circular. So now I'm starting to optimize it for assembly. So the measurements change as the lines, or the tips of the fishing lines that I use to assemble those tend to undo themselves, and then it creates this kind of puffed end. And so I adjusted the system so that I would optimize that and make it much easier to assemble. I also simplified it to some of its minimum, and so I used 3 here, so to maintain a proper axle. If I had only 1 string to connect those, there would be an issue about spin, since if the joint was not extremely tight, there would be some sway in the thing. Now if I have 3, there's a lot more sway, so this is one of the ways to optimize it. This is a very functional joint, so I could put that in part of a mechanism and it would work super well. I can tie it with the back channels, and this is a very functional joint. So it took me, this is the 7 one, so it took me 7 to get something that was quite functional. Let's go further. Now I did a few different tests on this one. Is a V2, but I did a lot of different tests. You can see the complexity of the drawing now is a lot more intense than the other one. So now I wanted to move into the phalange. So this one is one of the first phalanges that I made. This is a phalange connection between one of the knuckles. So this would be like the end of the first phalange, and that would be the start of the second. And this pattern would repeat itself. I'm not sure if I have. Hold on. Yeah, okay, so what you do basically is I'll create a rectangular pattern, so to have multiple parts, and I'm gonna assemble this piece with this piece. So just copy paste this at the end and connect it both two, so it's like an endless loop. So this is just one of the connections. Now this one here, I wanted to add a little bit more degrees of freedom. So you can see here that the profile of the channels are a little bit different. They have this outer curve, and there's this outer circular profile with this flat panel. This enables a little bit more degrees of freedom, where there's a tilt that can go something like 30 degrees on each side, and then it can go up to 90 degrees on top, and then it will use this as a stop. So this is very useful. Now I passed a bunch of strings in here so you can have different connections. One of the things I wanted to test on this one was how I could use side channels in order to create a pull and push systems where I can bend the part by pulling on specific channels. However, because this one is very thin, it was difficult to have vertical or lateral movement on the part by using the strings because the channel didn't operate properly. So I had to optimize that. But this is also a functioning joint. It's useful, but it's not the best. I've got some better ones around. This is 8, so let's go 9. So we got to the 30-minute mark. I've got some more coming up. It's gonna maybe take 45 minutes to go through all of it. I did a lot of parts. In the last couple of months, I must have printed more than 200 parts. So this one here is one of the final iterations of the tendon and bone connections. This one, there's a few other ones that are interesting, but it's one of the last. This is a very functional model, so this can be 100% used in a robot to make a hand. The connection here are done effectively, so these 3 different lines connect these 2 parts so that they don't move, and I also have these side channels here that enable me to have control over the bending of the parts on each side. So this is a very functional part. I've got a few of them printed already, but I just need to figure out other systems before I can move on with the rest of those ideas. But this is one of the final shapes of all the exploration that I did, and this is version 10. Now in the tendon and bone, I also wanted to have different types of systems. This is, you can see, it refers to that printable bearing system, but that you can assemble or pass different bars through, and you can make it secure with strings. So this is another iteration. Oddly enough, this is one of the first one that I thought about when making the tendon and bone, but I didn't manage to translate into shape until iteration 11, which is kind of surprising. The tendon and bone joinery, the 13 I think I made, it took me about 2 days to come up with all of them. 2 or 3 I think, maybe, I think 2. So yeah, this is I think the final iteration of the phalange bone. Those are the ones I printed. I just I took out some of the connections, simplified it, added a bevel, and I also added a channel here that you can see. This would enable me to connect different parts and have them fold up and down. Though these channels on the side would allow me to have control over the lateral movement. So this is kind of an omnidirectional phalange, so I can spin it in every direction that I need. I just print a bunch of those, and then that's what I got. Okay, so that's going to be it for the phalange or the tendon and bone connectors. Next up, so vast failure, I'm going to be talking another system, another video. So the next one is a cyclodal drive. So I'm working on a system of cyclodal drive that utilizes pulleys. I think I had an issue with this one. Hold on, cyclodal drive 2 is maybe up there. Yeah, so okay, cyclodal drive 2. Now I'm getting to the more recent one, so I still need another 10 minutes at least to finish all that. So you can see all the things in here. Canvas destruction. So I did a bunch of iterations, so I didn't get this one on the first try. I had to try it a bunch of times, and there are still things that I need to figure out on this one. Noticeably is the pin diameter changed from the first sketch to the last print. That's not right. So I started with this diameter for the pins, which is a radius of 5 millimeters, and then I changed because it turns out that it's better to just use the straight 3.5 millimeters for the pins, because I can assemble it with bamboo skewers, and so I create this circular pattern like this carrier here, and I can relate like a bunch of different bamboo lines, and it creates this outer shell that's really solid for 3D print. So hold on, where is my, okay, so that's the gear, or the lobe. That's the final design for the lobes. Now you can also see that I've got these pulleys in here, and that is a very specific thing about the cyclotral drive. Now I'm wondering if I should start a new video, because these are the more recent projects that I've been working on, and they do deal with kind of a different level of understanding. So you know what, I think I'm going to stop it here and start a new video for the next part, so to separate a little bit, since this work I just reviewed in this video was maybe during March through April, and the next one is going to be more about the end of April and May. So I'm going to stop it here. It's been 35 minutes, so I'm going to move on to the next video. So thanks for your time and attention, and I'll see you soon.